Hello and welcome back to sunny Milwaukee here on the beautiful campus of Marquette University. So today we're going to talk about irrotational flow of a Rankine body, and this follows on from our discussion of Rankine flow over, irrotational flow over a Rankine half body. So let's get started. The objective today is to continue in our series of more complicated flow fields by looking at the doublet. We looked at the Rankine body, a Rankine half body, and today we're going to combine a free stream with the doublet to form the Rankine body. So that's basically flow over a circular cylinder. If you look in the literature, this is often called the Rankine oval. So you'll see it listed either way if you go look it up in a book or so. But all of these are built from the basic building blocks, which is flow over uniform flow or source in a sink or the vortex. All right, so recall from when we derived the doublet solution several lectures ago, we got this form, the streamline in Cartesian coordinates or in cylindrical coordinates, and then we got the potential function in cylindrical Cartesian coordinates or cylindrical coordinates. And together, this doublet is also known as the dipole. So this represents this dipole that you're used to seeing, like the magnetic field of the Earth. So in order to get flow over a circular cylinder, we superimpose the free stream over the dipole. And so here it is mathematically in both Cartesian and cylindrical coordinates. Here's our free stream. And then this is our dipole at the origin. Here's an image of both of them together. And then when we look close to the body, this is what we see. So we see that the dipole is still in the center on the origin, and that the free stream has come in and met the dipole and forms this closed circle here, right? So this is our circular cylinder. And it's important to recognize that this is in fact a circular cylinder and not a sphere. That's a very different solution. So there is an inviscid flow solution over a sphere. That's a different ball of wax, so to speak. But we won't cover that today. So keep in mind, this is a planar solution in the XY plane, and it extends in the Z plane forever. So it's basically an infinitely long circular cylinder. All right. So you can see here that the dipole moment created this streamline that propagated upstream and met this psi equals 0 streamline. And they basically formed a saddle point. So two streamlines come together, and then they emit two streamlines. And so this streamline comes around here, and you get here. So you get this closed cylinder. They meet again at another saddle point, and one of the streamlines proceeds inward towards the origin, and the other one proceeds downstream. So this forms the basic circular cylinder. We think of this as flow over a circular cylinder, although we could pick any streamline to be, quote, the solid surface and think of flow over that solid surface. So for example, I could pick this streamline right here, and it looks like maybe it's just like some sort of bump or something, some sort of bump. So I can imagine that I might want to know what the flow is over this bump, and then you could have all these streamlines above it, and that would also be a flow field. I could calculate the pressure on that bump or whatnot. So this particular flow represents a lot of different flows. All right, so just like we did with the Rankine half body, we can begin to go through and look at what this solution tells us about the velocity field and stagnation and so forth. So let's start with the velocity. Can we find the velocity? Well, I would think by now this is getting to be kind of old hat. So if we have the stream function here, which I wrote as the free stream velocity times r minus r squared over r sine theta. So I'm working in cylindrical coordinates, and I've gathered up this collection of terms here to represent the dipole strength. And let's recall what that is. Remember what the dipole is. We took a source and a sink, and they were initially separated by this value epsilon, this value eta that you see here. And then I allowed them to come together, but when I did that, I had to continuously increase the strength of the source in the sink while holding this V dot times epsilon constant so that the two didn't annihilate each other. And in so doing, they came together and formed this dipole that you see. So I collected these terms together as a squared. Now, if I want the velocity, I just take the derivative with respect to theta times 1 over r to get the scalar quantity u of r, and to get the scalar quantity u of theta, I just take the derivative of psi with respect to r. So it's easy enough to do here, right? The derivative of this function with respect to theta, sine just turns into cosine. The derivative of this function with respect to r, I get r goes to 1, and I get that r raised to the minus 1 becomes minus r to the minus 2. So here they are. This is, in fact, the velocity field, and it describes the velocity everywhere, in the cylinder, outside the cylinder, over the whole xy plane. Can I find the stagnation points? Well, let me go back for a second. So I have written here this, this velocity gradient, and let's see here if this makes sense. 2u on the cylinder, right? And so this would be at what? Cosine equals to 90, and this is really u theta here. So u theta is equal to 90 degrees. The sine becomes 1. And as we will show in a minute, the radius of this cylinder is this r. So this would become 2r times u infinity. So we get the magnitude 2r u infinity. All right. Can I calculate the stagnation points? So the stagnation points are the locations where the velocity field goes to 0. So I simply just have to set the velocity that we just solved, those two terms, equal to 0, and then solve for the r and theta locations. I have two equations, and I have two unknowns, theta and r. So when I look at this first equation, u of r is equal to 0, I have three terms multiplied by each other, this term, and this term. One or more of those terms must be equal to 0, must be the culprit, in order to force all of them to be 0. So u infinity can't be 0, or I wouldn't have flow over a circular cylinder. So either 1 minus r squared over a squared over r is 0, or cosine theta is 0. Cosine theta is 0 at what? Pi by 2 plus or minus pi by 2. So that's how I get this. And then 1 minus a squared over r squared is 0 when a is equal to r. So I get this guy right here. All right, so when I look at u sub theta, and I think about those three terms multiplied by each other and who is the culprit here, again, u infinity cannot be 0. This 1 plus a squared over r squared, that's always going to be positive, isn't it? Those squareds make it positive, and then you're adding that to a positive number. That's never going to be 0. So just the cosine theta is going to be equal to 0, or just the sine theta in this case will be equal to 0. And theta is 0 or pi for the sine function. So when I compare these two, the second equation, the u theta equation, didn't tell me anything about r, right? And so if I want to know where the flow is 0 with respect to r, I have to take this bit right here. So it's going to be 0 at r is equal to a. And also, if I want to make u theta equal to 0, I can only pick theta as at 0 or pi. So together, I get the idea that the stagnation points only occur at theta is equal to 0 or pi, and at r is equal to a. And I have two stagnation points. Now, in the Rankine half-body, we just had the one at the leading edge, right? And here it's kind of obvious from the picture that I have these two stagnation points. And the math bears that out, right? So the stagnation points are the fore and aft stagnation points. Now the fore stagnation point is very obvious. I mean, all bodies have this leading edge stagnation, but the trailing edge one is a little trickier, and we'll talk more about that in the next couple of slides. All right, so what's the stagnation streamline? Well, by definition, it's the streamline that passes through the stagnation points. Now, in this particular flow field, one streamline passes through both stagnation points, but that's not necessarily the case. You could have multiple stagnation points in your flow field and multiple streamlines that go through them. So in this case, we can determine what the value of the stagnation point is by just letting r go to a and theta go to 0 or pi. And in the limit, it's easy to see that, let's see, as r goes to a, right, this becomes r squared over r, so this is r minus r is 0. And then sine theta, either at 0 or pi, goes to 0. So this is well behaved, and we just learned that the stagnation streamline is 0, just like we've got drawn here, so it was a little bit obvious. So it's different than the Rankine half-body, right? The Rankine half-body, the stagnation line was defined by the source strength per unit length divided by 2. Okay. Is the stagnation streamline a circle or some other shape? Well, it looks to be a circle, right? But let's prove it definitively that it is a circle. And how might we do that? So the stagnation streamline is 0, and so I know what the function for all of the streamlines are. So if I select just the stagnation streamline, I get this expression right here, right? U times r minus a squared over r is equal to sine theta. Now, it is true that this part of the equation is 0, but it's only 0 when a is equal to r. And this one is 0 only when theta is equal to 0 or pi. Now, if we're looking at the whole body, if we're going all the way around, theta is not always equal to 0 or pi. Theta can vary between 0 and 2 pi, right? So we're going to have to rely on this part of the equation to always make the stagnation streamline 0. So I can just write that part here and set that equal to 0. And then solve for the value or the relationship between a and r. And it turns out that r has to equal to a in order to make that relationship always true. And we know from the previous slide that I had written what the value of a is, and that's a constant. So r is equal to a constant is the definition of a circle. So for sure, this Rankine body produces flow over a circular cylinder. You know, I was quite old before I realized that the word cylinder doesn't imply a circular cylinder. You can have a square cylinder, or you can have an elliptical cylinder. It is more exacting to say circular cylinder. All right. So now that we know what the value of the streamline is, the stagnation streamline, that's the one on the body, we can calculate what the pressure is on the body. That's a very thermodynamic, fluid mechanic thing to do, calculate the pressure. So can we calculate the pressure? No problemo. What we need to do is insert the relationship between r and theta that describes the shape of the body into the velocity field so that we get the velocity just on the body, and then we take its magnitude and shove it into the Bernoulli equation and get the pressure. So here's the velocity field. We know that the functionality, the relationship, is that r is equal to a for all theta. So I can insert that into first the scalar u of r term. So when r is equal to a, this becomes 1, and that becomes 0. And so the radial velocity along the surface of the cylinder is always 0. That makes sense, right? It's just theta velocity along the cylinder, right? Because it's a circle and there is no radial velocity. You can also think of it as it's a streamline. So the streamline can't have a velocity component normal to it, right? By definition, it's always tangential to the surface. And in the cylindrical coordinate system, that's r is equal, or u of theta. So let's put in our definition for u of theta. Let's put in our definition for the cylinder. 1 plus a squared over a squared, that's 2. So we get sine theta of 2 minus 2u infinity, so there it is. And then I can take, or I can solve for the velocity magnitude q by taking the vector sum of u of r and u of theta. And so I just square it and take the square root, and so I get this positive quantity 2u infinity sine theta. So then I can just put that right into the Bernoulli equation, which last time we manipulated into the coefficient of pressure, 1 minus q squared over u infinity. So this becomes 1 minus 4 sine squared theta. And this is an incredibly famous result in the world of fluid mechanics. You know, this is really up there. This represents what? The coefficient of pressure around a circular cylinder as defined by inviscid flow theory, or irrotational flow theory. And this led to what's known as the DLambert Paradox. And so what is the DLambert Paradox? It is that if you calculate the drag force resulting from this pressure distribution, it is 0. Now we know that circular cylinders have drag. I mean, just stick your arm out of a car window next time you're driving down the street. Don't stick your arm out of a car window. Next time you're in a bus, stick your arm out of the bus window, and you can feel the drag force on your arm, right? So why is it that this beautiful solution we just derived with all of this physics ended up with 0 drag force? Well, it stumped DLambert, and here he is here. Here's a nice picture of him, a portrait. And you can see he's another Peruvian like Laplace, and lived the same time as Laplace, right? Maybe they were buddies. So that's kind of cool. And let's run through this paradox ourselves. So here's the coefficient of pressure. C sub p is equal to 1 minus 4 sine squared theta. And if we're going to calculate the drag, we need to get the component of the pressure in the drag direction. So remember, you have a circular cylinder. Pressure always acts, our sign convention is it acts inwardly normal to the surface, so the pressure acts pushing on the surface as such. And then if we want the drag force, that's the force in the x direction, so we need that component of the drag force. That's the cosine theta component of pressure. Then we need to multiply it times the area to get the force. And the unit area in this case is r dz d theta. That's the unit area on a circular cylinder. And since we are talking about confining ourselves to the surface of the cylinder, and we know the radius is a, I just inserted it here. So it's a dz d theta is our unit area. We're integrating pi over cosine theta around the circular cylinder, so theta goes from 0 to 2 pi, and then some depth into the board, 0 to z naught, so that's some sort of unit length. Now, this is not so hard to do. I mean, here's your expression for pressure right here. Here's the function. You just take this and shove it in there, and you integrate. It's pretty easy to do. So this being such a famous result, I think that we'll take a little coffee break here and let you try this yourself. Coffee. I'd give this a 2 bean difficulty. It's not too bad, really. The bottom line is, though, that you get 0. So that is rather paradoxical. Why do you get 0? DLambert himself wrote this, it seems to me that the potential flow theory developed in all possible rigor gives, at least in several cases, a strictly vanishing resistance, a singular paradox which I leave to future mathematicians to elucidate. Future mathematicians, that's us. So that's pretty cool. What is the solution to this paradox? The answer is boundary layer theory and separation. So it wasn't until the early 1900s, right, that Prandtl came along and really cemented this idea, convinced everybody that the boundary layer was a real thing. And we'll talk a lot about boundary layers later in this course, but not right now. And the other thing that's more relevant to this discussion is this idea of separation, which is amazing to think that those guys back in the mid-1700s had no idea of separation. It really required experiments, right? Careful experiments to go into wind tunnels or whatnot and look at it. So let's look at how separation affects the drag. So here's the plot. Here's a plot of the pressure coefficient from our ideal flow solution. Cp equals 1 minus 4 sine squared theta. You can see it starts off at the leading edge at 0 at our stagnation location. And the coefficient of pressure there is 1, as we discussed. So it's the sum of the kinematic pressure, the dynamic pressure plus the thermodynamic pressure, the total pressure, right, stagnation pressure. It's equal to 1 because we normalized it that way. And then and the velocity there is 0. And then as the velocity increases, as we move around the cylinder, the velocity increases, the pressure decreases, right? So the pressure drops all the way down to some minimum at 90 degrees, the maximum velocity being 2u on the cylinder. And then it recovers back. This follows the same path up to stagnation again, the trailing edge stagnation where again, the pressure coefficient is equal to 1. So this is the ideal flow, right? Now, when you throw in separation, what happens is that the flow comes along and the velocity is increasing, but it's increasing in a positive pressure, right? Flow doesn't want to go into a positive pressure. It likes to go from positive pressure to negative pressure. So when it is forced to go into a positive pressure, we call that an adverse pressure gradient, right? So the flow resists that. So as a result, what happens is that somewhere along the line it separates, right? So it decides that it's easier just to come off the cylinder. And so we're showing separation here. Instead of the stagnation streamline following along, it actually comes off the body. This is real flows now, right? So back here you're left with this big dead region of flat pressure, as it turns out. Here you can see the data. This is wind tunnel data. The flow starts off at 1, and it follows the analytic solution for a while, and it deviates due to the growth of the boundary layer and this fact that the velocity on the cylinder is 0. And then it kind of looks like it's beginning to recover and come back up, but then the flow separates. So it looks to me like the flow separates right about 80 degrees, and then it just flatlines after that, right? So it's just constant pressure back here in the wake after about a little after 80 degrees. And so that's what happens for laminar flow, right? Laminar flow meaning the flow comes in laminar, it attaches to the body, it remains laminar as the boundary layer translates around the cylinder, and then it detaches. What happens if the flow is turbulent? So in a turbulent flow, the flow comes in, and within the boundary layer, there's lots of swirling and motion. And so this swirling allows the boundary layer to actually get around the body a little bit better. It's able to negotiate the turn before it separates. So when you look at the solution here, right, the solution comes around and it's better able to negotiate the curve. It gets around where the laminar flow separated, and then it begins to recover, and it looks like it's going great, and then whammo, I'd say right around maybe 130 degrees or so, the flow separates and just flatlines thereafter. So that results in more pressure recovery. Let's think about for a second what the integral means, right? So when we integrate this profile, we're taking the area here, the component in the x direction, and because of that cosine theta, we're subtracting it from the area under this curve right here. Cosine changes sign there, right, at 90 degrees. So when you take the integral, you're really comparing the area under these two curves. When you look at a flow like this, you have all of this area under here, but you didn't get as much under this portion after 90 because of the flow separation. So you end up with not as much pressure recovery and a net force in the drag direction, right? And so that's where the drag comes from, at least the pressure drag, right? As you'll find out, drag is made of two components, the viscous and the pressure drag. The pressure drag results from the fact that the flow separated, it didn't recover, and we didn't get all of this positive pressure back, helping to push the cylinder upstream, right? So that's where the drag comes from. Now, in the laminar case, because we got more pressure recovery, we had more area under this curve to fight against this area under the leading edge curve. So you have more force pushing back, and the result is less drag. So this pressure recovery is a good thing. And we try to induce that pressure recovery, actually, by putting dimples on golf balls, for example. It forces this flow to swirl locally and become turbulent, to better negotiate the ball, to increase the pressure behind the ball, closing the wake. So that's what's going on there. But this is a really complicated phenomena. You can see here that the laminar flow Reynolds number was 1.1 times 10 to the fourth, right? When we increased the Reynolds number, the flow naturally transitioned to turbulent, 6.7 times 10 to the fifth, over 10 times faster. The flow transitioned to turbulent naturally, and you got this pressure recovery business going on. But if we increase the flow even more, the net result is less pressure recovery. So we start to approach the laminar solution. So this is not monotonic in any way, so it infers that this is a very nonlinear sort of behavior. But we'll talk more about this in later lectures when we talk specifically about external aerodynamics. All right, so not all flows separate. This is an example of Healy-Shaw flow, and Healy-Shaw flow is also creeping flow. This is very, very, so you think about the Reynolds number, right? The Reynolds number is what? U times some characteristic length divided by the viscosity. And in this case, we're talking about diameter as the characteristic length. So to get very small Reynolds number, either you have to have tiny, tiny diameters like flow in your body around cells or microfluidics. There you can get creeping flow. Or you have to have very, very small velocities in order to accomplish this. Or very high viscosity, I suppose. So in general, we don't encounter these flows if you're talking about aerodynamics, airplanes or cars or flow in pipes. In general, we're at much, much higher Reynolds numbers, and we always avoid creeping flow or this Healy-Shaw domain. But it does exist. And I wanted to mention that this picture is taken from a very famous book. I happen to have a copy of it here. My advisor gave me this book when I graduated with my PhD. It's an album of fluid motion by Milton Van Dyke. And within this book came out pre-internet, right? So there are hundreds of pictures, flow field, just flow visualization. There's not a lot of text here. It's just picture after picture of various flow fields. The book is organized into different types of flow. So chapter in natural convection and various flows associated with natural convection. Here's supersonic flow. Flow over supersonic objects. So it's a wonderful book, and in the days before the internet, if you wanted to see these pictures, you had to trek over to the library to get a look. And I do have a Milton Van Dyke story. You know, Milton Van Dyke is an American, and he went to where did he go to school? I think he went to Harvard. And then he spent some time at Cambridge. So he was there when G.K. Batchelor was there. He was there when my personal hero, G.I. Taylor, was there. I mean, he could have known G.I. Taylor. That's unbelievable. So I have to say, the first time, I have a Milton Van Dyke story, the first time I went to the American Physical Society, DFD, that's the Division of Fluid Dynamics conference, they had an evening session that included an open bar, and so I went there. I was the first person there, and there was going to be a dinner afterwards. And so I was there, and then this grizzly old guy walked in, and I was like, wow, who's this, you know? And we got our drinks, and we started talking, and then we sat down together, and then his old buddy friends all sat down at the same table, and it turned out that it was Milton Van Dyke. And all of those guys around the table were his contemporaries, and it was really great. I sat there and got to talk with those guys about all of their work, and it was fantastic. So getting to meet one's heroes is always fun. All right. Let's talk about flow separation. Back to flow separation. So we were talking about the differences between laminar and turbulent flow separation, and here's a good example. This is from a wind tunnel, and we're looking at a sphere that's on a sting. You can see the sting behind it here. There's a stick holding this sphere up, and wind is blowing in this direction, and we're illuminating the flow with a smoke wire. And a smoke wire is much like the hydrogen bubble technique. Take a wire, but you have to coat it with oil or something like that. Then you apply a voltage and you turn that oil into smoke, and then just for an instant you get to see this smoke field. You take a photograph of it, and boom, you get something that looks like this. So here in this case, you're looking at flow over a sphere. This is this is laminar flow. And then if I asked you to guess where you thought separation occurs, you might look at this and reasonably say, well, it looks like there, right? That looks about like where the separation occurs. So you can see the smoke in the boundary layer here, and then it separates about right here, and you're left with this wake, right? And there's air in this wake. It's not like it's a big void. It's just a bunch of swirly air back here that is kind of dead air at some constant pressure. Now, if I asked you to measure what that angle is, you see it's just over 82 degrees. That's what we saw in the previous plot when we looked at the data, that the pressure as it recovers flatlined it at about 82 degrees. Now, if we go in and we trip the flow, meaning we put a trip wire in, so the wire is placed about here on the cylinder, and what that does is it comes in and it's laminar, so it's the same Reynolds number. The flow is laminar, the boundary layer is laminar, it hits that wire, it trips, and it begins to swirl, and it swirls, and it swirls, and it's better able to negotiate the cylinder. And it's pretty obvious from this picture that the wake here is what? It looks maybe like something that big, whereas the wake here looks much, much larger. So the one with the narrower wake is going to have the less drag. So where does separation occur here? Where, well, if we were generous, we would say, well, maybe it's about right there. That's where I can really see smoke in the boundary layer, right? So if I measure that angle, that's about 120 degrees. If you look at the previous plot, it looked like, according to the data, it was more like 130 degrees. So whatever, you know, it could be a little bit further back. But the bottom line is that delaying the separation reduces the pressure drag, it closes the wake, it allows the pressure to recover, reducing the pressure drag, but you do suffer a little bit by inducing this turbulent flow and increasing the viscous drag. But the net result is lower overall drag. The pressure drag, the reduction in pressure drag is greater than the increase in viscous drag. Again, we'll cover this to a much larger degree later. I'll go ahead and show you some fun pictures of flow separation. This is a classic picture, much like the previous one. This looks like a modern version of the previous picture. Looks like the wake behind a Seawolf submarine here. You can see the wake, the turbulent wake. Flow over a golf ball. This is a picture taken by Peter Behrman, who I got to meet also. I met Peter Behrman when I was in grad school. I was working in the wind tunnel, and he came in, and we were all in awe. There was Peter Behrman, and he looked at me, and he said, I was holding a wrench, and he said, I never let my students have wrenches. It was a monkey wrench, right? I never let my students have monkey wrenches, a crescent wrench. I thought, that's it? That's all I get from the great Peter Behrman? Anyway. Here is flow over a car. You can see that the wake is here. There's a definite deflection in the streamlines behind the body. This is a picture I took out in White Sands, New Mexico, back when I had a real job working for the Navy. We would test our supersonic rockets out there, and you can see the wake illuminated by the density gradients in the compressible flow regime. So that's pretty cool. And this is a video taken from, I love this video series. It's from the National Committee on Fluid Mechanics. And you should really Google those and YouTube them and look at them all. They are wonderful videos. It's a good time. So what I recommend you do is maybe find somebody special, like a little date night, and you watch these videos together because they are fantastic. What you're seeing here is this airfoil, and you can see as it begins to pitch up, you can see the wake begins to get larger and larger, and you can follow this separation line as it moves closer and closer to the leading edge, and we form a larger and larger wake, and all the time generating more and more drag. All right. Here's a CFD solution showing the ideal flow over a circular cylinder. You can see that it's kind of symmetric fore and aft. I think the cylinder's been colored by velocity, not the cylinder, the sphere. And that's not what real flows look like. Actual flows have this wake, right? And so here is a flow over a smooth sphere on the top and flow over a dimpled golf ball on the bottom. And you can kind of see, if you believe, that the wake has been closed somewhat, a narrower wake for the smooth versus the rough sphere. All right, so that wraps up our lecture on the Rankine body. So now we've covered the doublet, the Rankine half body, and the Rankine body. And next time we're going to add circulation to this solution. So we're going to add a vortex. And what that'll do is generate a side force that we call the Magnus force. So until then, we'll see you again next time. All right, take care.